everybody. I hope you guys are having a good day. I'm going to be teaching you a topic today called percent yield. So if you guys would, there are a few things that I want you to have out in front of you. I want you to, of course, have your periodic table, your calculator, and also I want you to have worksheet 8.4, which has some very, very brief notes on percent yield, today's topic, and a whole bunch of practice problems, okay? To be quite honest with you, most of what is in these practice problems is practicing skills that we've done before. The new content that I'm going to teach you right here is actually very quick and very simple. Okay, but we're going to work some problems together. So let's get started. All right, so as I said, today's topic is something called percent yield. Okay, and there's a little bit of vocabulary, and these terms are in bold at the top of your notes. And the first term that I want us to look at is the term theoretical yield. Okay, guys, the word yield means how much product can you get? Okay, and that's going to be more specific, how many grams of product can you get? That's what the word yield means. Now, theoretical yield, the word theoretical, if you think about how you use that in your everyday language, where you might say, well, theoretically we could blah, 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 meaning like if everything was perfect, we could do this. Theoretical yield is the amount of product that you get when you run a reaction, assuming that everything ran perfectly, that there was no error. It's the most product you could possibly get. Now, of course, we live in the real world where there is error, okay? And so another vocabulary term that we need to know is something called actual yield, okay? Meaning you go into the lab, you run this reaction, you measure the mass in grams of the product that you have created, and using actual circumstances where there is error, where there are things that go wrong, okay? And percent yield is when you compare those two numbers, okay? Percent yield, the formula for percent yield is your actual yield, how much you actually got, divided by your theoretical yield times 100%. Now, the way that these problems are set up, the actual yield will almost always be given to you. I want to tell you that you will never, ever be given the theoretical yield. You will always have to calculate it yourself using stoichiometry. Okay, and I'm going to show you what that looks like. Okay, what are we talking about? You actually already know how to do this. You just don't know that you know how to do it. All right, so on your notes, you have an example, and I'm kind of hoping that this example looks familiar to you. Because if you guys look on your limiting reactant notes, the worked out example on the front of your limiting reactant notes is this same exact problem, where we were given 45.5 liters of hydrogen and 23.1 grams of nitrogen. And on your limiting reactant notes, we used those two values to figure out which reactant was limiting, okay? And if you go back and look at those notes, we found that hydrogen, H2, was our limiting reactant. So knowing that now, okay, and you'll notice in your notes it says using your limiting reactant, which has already been solved for in our previous notes. We're going to solve for the substance you are measuring, in this case, ammonia, okay? You'll notice that in this, the way that this problem is phrased, it says, what is the percent yield if 18.4 grams of ammonia are actually produced? Remember what I said? You're going to have to calculate the theoretical yield. So what does that look like? Well, if we know that hydrogen is our limiting reactant, okay, because we have already previously figured that out in our last set of notes, I'm going to use the amount of hydrogen to calculate how many grams of ammonia, our product, will be made. And guys, that number, 23.1 grams of ammonia, that is, whoops, let me go back, 23.1, that is, let me circle it, okay, this number right here, that is our theoretical yield. Okay, remember what I told you. You will always have to calculate your theoretical yield using stoichiometry. Okay, and if you're wondering, you know, well, how did you know not to use 23.1 grams of nitrogen, the other reactant, to calculate the theoretical yield? Remember, guys, the nitrogen, we previously found out that the nitrogen was our excess reactant. We don't ever use the excess reactant to calculate amount of product because that's not a correct number. We always want to use our limiting reactant to calculate the correct amount of product. So this number at the end, 23.1, that is our theoretical yield. Okay, and then, let me move this out of the way. Okay, they gave us the actual yield, so actual divided by theoretical times 100. Let's round percentages just like we've done before. Let's round them to 1 decimal place. Okay, and that's it. I mean, that just this last calculation is really the only new part to this. Okay, so let's look at a couple of sample problems. All right, under where it says homework on the front of worksheet 8.4, let's look at number 1. Okay, I'm going to work 2 problems with you. So this is number 1, and I'm just going to copy over the equation. Whoops. Okay. I want you guys to notice that there are no coefficients written in there, so you have to check. If you don't see any coefficients, you need to make sure that it is balanced, and this one is not. So I'm going to put a 2 there and a 3 there. Now it is balanced. Okay, continuing on. It says solid silicon dioxide reacts with solid carbon to produce solid silicon carbide and carbon monoxide gas. Okay, cool. There's our reaction. If 50 grams, I'm going to write that above, of silicon dioxide actually produces 32.2 grams of silicon carbide, what is the percent yield? So guys, that 32.2 grams of silicon carbide, that is the actual yield. In order to find the percent, I need to find the theoretical of that same compound. I need to find how many grams of silicon carbide can theoretically be produced. Okay, so this is just a straightforward stoichiometry situation. 50 grams of silicon dioxide, and I'm going to convert that into grams of silicon carbide. Okay, and I'm going to plug all that in, and it comes out to be 33.4 grams of silicon carbide. Okay, that number that I just found, that is my theoretical yield. Okay, stoichiometry tells us the maximum amount of product I could possibly get. Okay, and that's 33.4. The problem gave us the actual yield. So to calculate percent, we just divide actual by theoretical times 100. Put that into your calculator, you're going to get 96.4%. Okay. And guys, if you think about it, what percent yield represents, it's kind of like putting a number on how good your lab skills are. You know, if you run a reaction in a lab and you do really well and you're very careful and you minimize error as much as possible, you should get a percent yield pretty close to 100. And when you all go on to college, those of you that take any sort of lab science, a lot of the lab science courses will have you calculate a percent yield at the end of every lab. And if you get below a certain percentage, they will actually make you redo it. Okay. Now, I'm not going to do that, but that's kind of how it works in college. Okay. Anyway. So what I would like to do now is I want to work through another problem with you, but I'm going to sort of give you a little time to work on your own first. Okay, so what I want you guys to do is look down at number 3, okay, at the bottom of the page. So I'm going to give you a little bit of time to start it on your own, but I'm going to introduce it to you. Okay, so we have a reaction in number 3, and actually let me just pull that worksheet up. Okay. All right, so let's look at number 3. So we have a reaction given to us in number 3, and I do see coefficients. So guys, you may safely assume that it is balanced, okay? And the problem says a 75-gram sample of iron is mixed with 11.5 liters of oxygen at STP. Letters A and B should look really familiar to you, okay? Because these are topics we have already covered. Letter A wants you to identify the limiting reactant, and letter B wants you to determine the amount of excess reactant that remains. Remember, guys, the thought process when you're determining a limiting reactant, okay, is I'm going to take each one of these given pieces of information and I'm going to convert it to an amount of product, and I'm going to do the same thing with the other given piece of information. Now here's my recommendation. Look at letter C, okay? Letter C asks us to calculate grams of the product. Now you don't have to go along with me on this, but when I'm doing my the math that's required in letter A, I'm going to go ahead and convert both of my given values. I'm going to go all the way to grams of the product, and then we'll take it from there. Because the reason I'm saying that is because I know in letter C, I'm going to have to go to grams anyway. So I'm just going to go ahead and do that in letter A. So what I want you guys to do is pause the video and do letters A and B, because that is review material. And then unpause and we'll check your answers. Okay, so I'm going to show you the answers sort of piece by piece. Let's just look at letter A. Okay, so as I said, I took each of the individual given values and I went all the way to grams of the product. I can see that the second calculation gave me the smaller amount of product. Okay, right here, let me change color. Okay, but what letter A is actually asking for is which reactant is limiting. Since I can see that oxygen gave me that smaller amount of product, remember that means that oxygen is the limiting reactant. Okay, so when letter A says support your answer with calculations, these are the calculations we would need to see to support the fact that oxygen is limiting. Okay, now that we know that, what is the other reactant called? Iron must be the excess reactant, and that's the one they're asking me about in letter B. So pause your video and see if you can do that calculation, something we did in a previous lesson. Okay, so let's look at part B. Okay, so I'm down here. Here's part B. Okay, this was part A. What I have done in part B, to refresh your memory on this, okay, I took the amount of product, the smaller amount of product, the correct amount of product that we were going to get of the iron oxide, and I converted it back to the excess reactant, which is iron. This number right here represents how much iron was used, was consumed in the reaction. And then from there, down here at the bottom, I know I began this reaction with 75 grams. I consumed 38.2, which means that I have left 36.8 grams left unreacted, in excess. Okay. Now, letter C, we've actually already solved. Letter C says calculate the mass of iron oxide produced when the reaction proceeds to completion, and in parentheses it says theoretical yield. Well, guess what, guys? This number that I have in a red box here, that is my theoretical yield. When you do a limiting reactant calculation, your smaller answer, the smaller amount of product, is the theoretical yield. So I already have my answer for letter C, done. There's the theoretical yield. Last part, part D, says if 42.3 grams of iron oxide are actually produced, what is the percent yield? So let me get to a fresh screen here. So this is letter D. The percent yield is the actual yield, which they gave us, over the theoretical, which we calculated, times 100, and there is my percent yield. Dun, 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 dun. Okay, so So will every percent yield problem involve limiting reactant? No, they won't. Some do, some don't, okay? You'll notice that on this particular worksheet, a lot of them do. That's really my way of kind of forcing you to have a little bit more practice with limiting reactant while also bringing percent yield in as well at the same time. I'm sure you appreciate that. Okay, so that is it, okay? I want you guys to work a couple more problems. Work together, see if you guys are getting the same answer. To finish this worksheet is homework, okay? And we will check it when I see you next in class. So I hope you guys have a great day, and I look forward to seeing you soon.